Alright, so I want to talk about obliquity, which is the tilt of Earth's axis. Okay, today they say that Earth's tilt is 23.4 degrees, and then in the future it will be 22.9 degrees, and this will be pointing towards Vega then. If we were to use their values for the greatest angle, let's take the limits. So 24.5 degrees and 22.04 degrees. Okay, if we set those limits to the width of the great year, so in other words, when the planet is at this position, it's got its greatest angle, and when it's at this position, it's got its least angle. So we'll use those limits. And so let's subtract these two from each other to find the mean. So if we subtract 4,619 degrees. Now, that's the maximum amount of tilt between these two. That's the difference between these two limits of obliquity. Half will be on this side of center, and the half will be on the other side of center. We need to divide 2.4619 in half, so that will give us 1.23095 degrees. So in order to come up with the mean tilt, in other words, the constant tilt of Earth, we would need to take the mean. There's a maximum tilt and a minimum tilt. The center line is the mean tilt. So we'd have to add 1.23. Well, we subtract 1.23 from 24.5. And on this side, we'll add 1.23 to 22.04. And these will give us the same number. And that number will be 3.27345. That works out for both sides. So 23.27345 is Earth's mean tilt. Now what am I saying? So what I'm saying is, now that we've established the mean tilt of Earth is 23.27, if we take that as being a constant tilt of Earth's axis, then a way that we could determine how much tilt there might be in the great year, the way we could determine that is we could just tilt that slightly. So this tilt would be 24.5, and the tilt on this side will be 22.04 degrees. Now, does that make sense to people? The Earth's tilt is constant. There's no wobbling or perturbations from other bodies in the solar system. It's an illusion because this orbit is not flat, it's tilted. I hope that makes sense. So here's a representation of Earth in its great year orbit. And as you can see, and I've demonstrated this in other videos as well, as anything circles the center, its orientation towards the center doesn't change. That remains constant throughout its total orbit. It doesn't have any capacity to alter its orientation. In this instance, this is representing the great year. As you can see, the tilt angle isn't changing. If we put this orbit on a slight tilt, now that the Earth is on a slight tilt, Although we know this angle isn't changing, this is going to give the illusion that it is. So simply geometrically speaking, that would be the max right there. Once you get up to the center point right there, that would be the mean, and then right there would be the minimum. You come back down, you reach the mean again, and you go back out to the max. The actual obliquity never changes. It remains constant. So I wanted to try to find out if we could use this method to figure out a date. And I think we can. So what we're going to look at right here is only this quadrant. So let's assume this is the limit, the greatest limit. And so we're going to look at this 90 degrees here. I put 90 tick marks out here on the circumference of this. I had 1 degree all the way around to the 90 degree mark. So 90 degrees in this part of the pie, so to speak. The reason why I use 1 degree is because if we know that using Simon's numbers, 51.136 arc seconds per year is the amount of precession, the annual constant of precession. Mainstream has it at 50.29. But let's just stick with the Tychos for now. And so in 1 year, we'll have traveled 51 arc seconds. So in order to travel 1 degree, we just divide 1 degree by the arc seconds. That gives us 70.4 years. About 70.4 years per degree. Hope that makes sense. So when I divided this into 90 degrees, that gives me the amount of time that it would take for Earth to traverse 90 degrees. And let's see what that is, 6,336 years. So to make this kind of simple, I just multiplied 70.4 times 10. So I did every 10 years instead of doing 90 tick marks. So more like 10 degree segments, 10 degree segments. So each one of these tick marks represents 704 years. Now, at first I was using from here to here. So I was using this distance to begin with, but the radius distance is not correct because Earth actually travels this circumference. So I was not getting the right answer because I was leaving out the amount of distance that it actually travels because I had it moving along simply the radius, which is not correct. You can't do that. What you have to do instead is you have to take each 100-year increment, and I'm just simplifying here. So as you can see, each one of these is 704 years, although the distance is unequal. That's because it's a compound angle. It says the Earth moves this direction, it also moves this direction if it began here. So it's got two directions are in play. So these 704-year increments are uneven. This would be a 704-year period, but it would appear that Earth had barely moved any distance. Then it moves a little bit more distance, then it moves a little bit more distance, and then when it gets down here at the bottom of the arc, it moves a great deal of distance reference to the plane. That's from this point to this point. That's 6,336 years. Hopefully everyone understood that. So you can use that technique to figure out where we're at So we're 6,336 years ago, we were at 24.5 if we used the limit. So that was the tangent of the orbit. That would be basically, if we had the orbit on flat, that we would be here. And so when Earth spins around and gets to the 90-degree mark, or the halfway point to the center, that's where the quote-unquote equinox would be. So it's equal here, it's equal there. It goes that way, it increases, goes this way, it decreases. We can figure out where we're at in time based on that. So if it takes 6,336 years to go from here to here, as we saw earlier, then we can figure out how long it will take to get from this point to 24.5 to this point, 23.44, at a 2.14% slope. And what I came up with is we're about, and this is exaggerated, but we're about 106 years away from, and these are using the Tycho's numbers. So we're about 106 years away to the mean obliquity. We're at 23.44 degrees today, and once we get to 23.27 degrees, as we climb up, we cross the halfway point. All right, well, hopefully that wasn't too convoluted. I'm sure it was. Please put any comments down below, and thanks for watching.